In the previous lecture, we have seen how to calculate, or we have derived a degree of freedom for a planar mechanisms. So, for planar mechanism where one of the links is fixed, degree of freedom equal to 3 into n minus 1 minus 2p1 minus 1 into p2, 1 p2, where here n is the number of links in a mechanism and p1 is the number of pairs that is those are having degree of freedom 1, and here p2 equal to number of the pairs those are having degree of freedom 2. So if the link is not fixed, then degree of freedom equal to simply 3 into n minus again 2p1 minus p2. So we derived these two formula, and we will consider some of the examples and see how to calculate degree of freedom of a mechanism. So first let's start with the 4 bar mechanism. So this is a 4 bar mechanism. This one is a fixed one, and let's say this is a link 1 and this is a link 2. Link 3 and 4, all these links are connected by a pin joint or hinge joint. So here we need to find out degree of freedom of this 4 bar mechanism, that is a dy of equal to our formula 3 into n minus 1 minus 2p1 minus p2, where here p1 equal to number of degrees of freedom or number of pairs having degree of freedom 1. So first let's find out the p1 equal to, so we have hinge joint between link 1 and 2. So here degree of freedom is 1 when we have a hinge joint, because it's a constraining, it's a translation motion in the x and y direction. So this link 2 can rotate only about this point O with respect to link 1. So the link 1 and 2 constitute a pair that is having only 1 degree of freedom. So 1 plus between link 2 and 3, again it's a constituting a pair having a degree of freedom 1, and between 3 and 4 again 1 degree of freedom, pair having the 1 degree of freedom, and again link 1 and 4 has a degree of freedom 1. So altogether how much? This is a 4. So here if I substitute in the equation 3 into n minus 1, how many links are there in this particular mechanism? 4. N is a 4 minus 1 minus 2 into what is the p1, that is a 4, and here p2 is 0. Why? Because there are no pair or no link pair having the degree of freedom 2. So p2 is 0 here. So how much this one? 9 minus 8, that is a 1 degree of freedom. This is as simple as this one. And for example, if this link 1 is not fixed, and if this link 1 is not fixed, this one is not fixed, then what is the degree of freedom in that case? So degree of freedom in that case equal to simply 3n minus 2p1 minus p2. Here p2 equal to 0. So again 3 into 4, that is the 12 minus 2 into 4, 8. So degree of freedom is 4. So what does it mean? So system, by fixing we already defined what is the degree of freedom. So degree of freedom is the possible movement of the link or output or input. For example, if you know the, or for a given input motion, if you want to find out how many output motions are possible, so we need to find out degree of freedom, and that's a turn out to be 1. For example, you need output motion of the link 4 in a required fashion, and we need to find out how many input motions should be given to, this input link 2 for a required or a desired output motion. So here also we can define the degree of freedom in that fashion also. So what does exactly this tells? So by For example, in this case, if you want to get say particular motion of the link 4, and if this link is not fixed, then we need to give 4 types of input motions. But whereas if you fix this link, these 4 types of motions that needs to be given to the input link for a desired output motion will be reduced to only one input motion. So that is the advantage of fixing this one. So that's why in all our most of the mechanisms we fix this one. And this question was asked in 2005 for 1 mark. This is quite easy one, straight one. So the number of degrees of freedom of a planar linkage with 8 links and 9 simple revolute joints. So whenever we say 9 revolute joints, all pairs are having only 1 degree of freedom. So it's a, what is the degree of freedom? Straightforward. So that is a 3 into n minus 1. Here they have mentioned also as a linkage. So whenever they mention linkage, that means one of the links is a fixed one. And what is the difference between linkage and a mechanism? Linkage is simply if one of the links is fixed one, then it's called as a linkage. And what is the meaning of the mechanism? So mechanism means to if you give a input motion to one of the links, then we will get definite output linkage motion. Definite means that the output linkage motion can be predicted or calculated for the given mechanism, for the given linkage. So if that is the case, then it's a that linkage is called as a mechanism. So here 3 minus n minus 3 into n minus 1 into 2 p1 and p2 is 0 because all the links are connected by simple revolute joints. So what is the value of this one? N is a 8 here. So 3 into 7 minus 2 into 9. How much? This is a 3. Answer is C. Next question is this one. This asked in 2004. This is a matching type revolute joint, and they have given degree of constraints, not degree of freedom, degree of constraint. We need to find out degree of constraint for each of this one. For example, if this is a spatial mechanism, this is not a planar mechanism. Okay, so for example, type of joint is, so there are 2 links, and these links are, first one is connected with a revolute joint. So for example, as usual, we will take ground as the first one, and this is the second one. The second one, so link 1 and link 2. So all except the rotation about the joint O, all other constants are imposed on this one. So here degree of constraint, degree of freedom is only 1, but degree of constraint is 5. So for revolute we have a 5. So for revolute we have 5 degree of constraints, and next one is a cylindrical. So if this is cylindrical, this is a hollow cylinder, fixed one, and inside this hollow cylinder we have another body like this. We have already seen that, and this is the body 1, this is the body 2, and this can reciprocate or travel like this to in this direction, and it also can rotate about its axis. For example, if this is the axis, it can rotate about its axis. So how many motions are available, are possible for this case? One translation and one rotation for the body 2. So how many degrees of freedom? Only 2 degrees of freedom. Then how many constraints are imposed on this one? 4 constraints. So cylindrical is the 4 constraint, and next one is the spherical. So in the spherical, I mean, as we have already seen, this is the groove, and inside the groove we have a spherical one. So this spherical is a this groove is holding the spherical. This is the spherical. So it cannot have a translation motion in any one of the 3 axes, but it can rotate. It can rotate about x-axis, y-axis, and z-axis. So it has a 3 rotational degrees of freedom, and 3 translation degrees of freedom are missing. So how many constraints there? So spherical is a 3 degree of constraints. So massive following. P is 2, and then Q is 3, P is 2, Q is 3. This is the one and R is the one. Answer is C. Our next problem is this one, asked in 1993 for 2 marks. So again, this is a 5 bar mechanism it's connected with the revolute joints. So again, this is a straightforward degree of freedom. Here n equal to 5, and what is the P? P is the number of pairs having single degree of freedom. So between 1 and 5 we have only 1 degree of freedom. So 1 and 5 constitute a pair, and degree of freedom that pair possesses only 1. And between 5 and 4 again 1, and between 4 and 3 again 1 degree of freedom, and between 3 and 2 again 1 degree of freedom, and 1 between 1 and 2 again 1. So how many degrees of how many pairs that are having single degree of freedom? That is a 5. So otherwise this is a simply no addition of all the revolute joints in this case, because at any given revolute joint we have only 2 links. If the links are more than 2, then we need to go for the formula j, what is that one, j minus 1. So here, since we have only 2 links at any revolute joint, then we simply add all the revolute joints. So that is a 5. So what is the degree of freedom? Equal to 3 into n minus 1, that is a 3 into 4, 12, minus 2 into p1, so that is a 10. So 2, answer equal to 2. For example, this is the link 1. For example, if we connect this one, that is nothing but link 1, and this is the 2, 3, 4, and this one is the 5. This whole triangle is a single link. So here again, what is the degree of freedom? So how many, all these links are only connected by a revolute joint. So whenever there is a revolute joint, then we can simply add this revolute joint, unless otherwise at any revolute joint if there are only 2 links. So in this case, what is the n? N equal to 5. So 5 minus 1 minus 2 into what is the p? So p is 1, 2, 3, 4, 5, 6. So 2 into 6. So how much this one? 12 minus 12. 12 minus 12. So that means degree of freedom equal to 0. This is the next example. Here we have three triangles, and these triangles are connected like this. So let's do numbering first. This is the picture 1, link 1, and this is the 2, and this triangle is the 3, and 4, 5, 6, 7, 8, and this triangle 9 and 10. Again this triangle is 11. So altogether what is the value of n? That is 11, and here we need to find out p1. So p1 is the pair having degree of freedom 1. So between 1 and 2 it's only 1, plus between 2 and 3 again only 1, and between 3 and 4 and 3 and 5, 1 plus 1. So this is over, this is over, and this is over, and this is also over. And next comes to this point, this point. So this particular point where 4, 6 and 9 are meeting, how many links are meeting at one revolute joint? 3 links are meeting. When 3 links are, the j links are meeting, what is the value of p1? That is j minus 1. So here j is 3, so 3 minus 1, and again at this point again 3. So this is over, and at this point again 3 links are meeting, that is a 5, 6, 7. So again j equal to 3. So number of possible pairs that are having degree of freedom 1 equal to j minus 1, that is a 3 minus 1, and this is also over. And here between 9 and 8 and 9 and 10 again 1 plus 1, 1 plus 1, and between 8 and 11 and 10 and 11 again 1 plus 1, and here again at the junction of links 1, 7 and 11 we have again 3 minus 1, that is a 2. So what is the total value? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. So what is the degree of freedom? Here P2 is 0 because there is no pair having degree of freedom 2. So this is 30 minus 2 into 14, 28. So what is the degree of freedom? 2. Next example is this one. Here we have two cams. These two are two cams. So first let's number these links. This is the one is a fixed one, and this is 2, and this is 3 and 4, and again this is the 5. So uh, before further going to calculating this degree of freedom, here I would like to explain how many possible motions um, between these two cams. So for example, this cam pair is equivalent to the gear pair, and for example, if you take a gear like this, so we have a gear tooth like this, and when this gear is engaged to the other gear, so this is again tooth on the other gear. So when this gear is rotating like this, so this will touch us here, and it's rotate this one in this direction. So when this gear tooth 1 touches this one, gear touches gear tooth 2, it not only pushes this gear in this direction, but it slides along this line. It slides along this line that we will see in detail when we are talking about the gears and gear trains. So how many possible rotation between a gear engagement, that is the one rotation, and as well as a sliding between these two gears. So here how many degrees of freedom between these pair? Pair means this is one gear and this is a gear 2, and if I consider this gear 1 and gear 2 as two links, there are two possible motions between these two links. So dy of between these two is 2. In the same manner, if I consider this cam also, for example, if I consider a cam like this, I considered a cam like this and another cam like this on this one. So when I am rotating this cam 1 in the anti-clockwise direction, this will rotate the cam 2 in the clockwise rotation, and at this point where it touches this cam 1 is sliding along this line, along the surface of the cam 2. So cam 1 is rotating the cam 2 and as well as sliding on this one. So there are two motions between these cams. So here also degree of freedom equal to 2. So whenever we come across any gear pair or a cam pair in our mechanism, then there the pair is having the degree of freedom 2. So let's go back to our problem. Here first calculate how many links are there. So links are 5, and next calculate the P1 pairs having degree of freedom 1. So that equal to this is the uh, this is the 1, and this is 2, this is 3, and here 4, and here 5. So we have a 5, and what is the P2? So how many pairs having degree of freedom 2? Only cam 1 and 5. So we can write P2 equal to 1. So let's substitute in the formula. What is the degree of freedom? That equal to 3 into n minus 1, that is the 3 into 4, 12, minus 2 into 5, that is a 10, minus 1 into P2, that is the 1. So degree of freedom equal to 1 for this particular example. This is the next example. Here let's number this one. So here in this case we have 5 triangles. So this is the triangle fixed one, fixed one, and this is a 2, 3, and a 4, 5. This is a 6, and this is 7, and this one is 8. So what is the value of n? 8. And in this case all are revolute joined. So here P2 equal to 0. So we need to find out P1. So what is the P1? So here this is a 1, and here this is again 1, and here also 1, and here also 1. So altogether 4, and between 4 and 7 again 1, 4 and 5 again 1. So 1 plus 1, 2. So this is over and this is over, and between 1 and 5 again 1, and between 5 and 8 again 1. So again 2, and then between 1 and 8 1, and only this joint is remaining. So at this joint we have 3 links. So when there are 3 links, what is the value of P1 here? So what I mean, how many pairs are there at the revolute joint here having the degree of freedom 1, that is j minus 1. So 3 minus 1 equal to 2. So P equal to 11. So what is the degree of freedom? Equal to 3 into 8 minus 1, that is a 7. So 21 minus 2 into 11, that equal to 22. So minus 1, degree of freedom is minus 1. So here if you observe, in some cases we are getting degree of freedom positive, and in some cases we are getting 0, and in this particular case we got minus 1. So when degree of freedom is positive, that means that particular given mechanism is having some definite motion for a given input. Or if you want to consider, if you want to have a definite output motion, then those many number of motions should be given to the input look equivalent to the degree of freedom of that particular mechanism. And when the degree of freedom, when the DIF equal to 0, that means that motion, that mechanism is not moving at all. So that particular mechanism is called as a structure. And when the degree of freedom is less than 0, or in this case we got minus 1, so this is called as a superstructure. So what do you mean by superstructure? For example, the same case, the same example, what I do is I just remove this particular link 6. Okay, so what I did is I just removed link 6, and again I will calculate the degree of freedom. So for this, now new degree of freedom, new DIF, I would calculate new DIF. So here again n become 7. So 3 into 7 minus 1, 6, minus 2 into P1. How much? P1 is how much? Here 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2 into 9. So it becomes 0. So in this case degree of freedom becomes 0. So for example, I want to make this particular mechanism as a structure. That means I want to make this particular mechanism as a degree of freedom. So I can take simply this mechanism, new mechanism. Why I unnecessarily consider this line? So, and if there are some particular structures where we need to provide extra links, so that even if some links fails, it still end up in the structure only, our degree of freedom is 0. For example, in the previous one we had degree of freedom minus 1, and for example if something happens and this link is cut or broke down, so in still this degree of freedom or it won't be disturbed, and still its degree of freedom becomes 0. So that is the advantage of superstructure, and these superstructures are generally used in bridges, and also in the upper part of the cranes. So there some extra caution should be taken while designing those particular structures, so that even if something happens or if some link broke down, still it maintains its structurality. Now we will consider some special cases. So this is the one example, and here links 1 and 2 are joined with the prismatic prismatic joints, and link 2 and 3 and 4 and 3 are connected using the sorry, link 1 and 2 are connected by using a revolute joints, and link 2 and 3 and 3 and 4 are connected using the prismatic. This is the prismatic. And when I say prismatic, we recollect, we have already seen in prismatic, we have uh, something like this, and here prism or bar is coming like this. So this has it can translate only like this. It can translate like this, and it cannot rotate. So what is the degree of freedom here? Only 1. So as like in a pair connected by the revolute joint, here also the pair connected by prismatic bar is having only 1 degree of freedom. So if I calculate degree of freedom using general formula, what happens? Here n equal to 4, and what is the p1? Here 1, here revolute joint between 1 and 2, so 1 p1 equal to 1 plus, and here also 1, so 2 plus between 2 and 3, so prismatic joint, so it allows only 1 degree of freedom, again 1 plus between 3 and 4, again 1, so this is the 4, so degree of freedom equal to 3 into 3 minus 2 into 4. So this is a 1, degree of freedom equal to 1. So this is just as like equivalent to the 4 bar mechanism. But here this is the wrong. Why? Because this is the in the link that we have between this prismatic bar. This can translate in this direction. So for example, if this link, we are moving this link or translating this link in this direction, but still if you observe, this whole structure or this one is not at all affected, or the if you give any motion to the link 3, there is no I mean there is no movement transmitted to the remaining mechanism. Otherwise, if this particular link can be moved without transmitting any motion to the other link, so that is something like redundant. Can we call this link as a redundant, because the motion of this link 3 is not affecting the mechanism, so we can call as this as a redundant. And whenever you have a redundant link in the mechanism, so this degree of freedom formula will be modified. So degree of freedom equal to, then in this case it becomes degree of freedom equal to 3 into n minus 1 minus 2p1 minus p2 minus fr, where fr equal to number of the links or number of the redundant links, a number of the redundant links in the mechanism. So if I substitute in this mechanism, what happened? 3 into 3 minus 2 into 4 minus 1, so this equal to 0, so degree of freedom equal to 0. So let's see whether it's correct or not. So if you observe here, if you rotate this one, and if you by intuition we can see that this is a locking, actually this is a locking this one, because here prismatic, if it is a revolute joint, then they can move, but if it is a prismatic, it can just no it will lock the mechanism, so degree of freedom equal to 0. So and we need to remember this formula. This is the final formula. This is the another example. Here we have cam set. This is the cam, and this is the circular disc. This is the circular disc, even though it's a little bit deformed. And these cam and circular disc are pinned to this cam is pinned to the ground link 1, with a revolute joint, and this disk is again connected to a link, and that link is pinned to ground using the revolute joint. And we have already seen the pair cam pair is having 2 degrees of freedom. And here what is the degree of freedom? Degree of freedom equal to 3 into n minus 1. How many links are there? 4. So 3 into 3 minus what is the p1? 2 into p1. P1 is the number of pairs having 1 degree of freedom. So between 1 and 2, 1, and between 3 and 4 again 1, and between 1 and 4, 1. So how many ones? 3 minus 1 into p1. So p1 is only 1, that is between link 2 and 3. So if you calculate in this manner, we get degree of freedom equal to 9 minus 7, that is the 2. But here this is the wrong. Why? Because we have already discussed, just now we have discussed, whenever there is a redundant link in the mechanism, then we shouldn't use this degree of freedom formula. Instead we should also keep FR. So let's investigate what could be the redundant link in the given mechanism. So if you look in this one, for example, if I rotate this link 3 about the O, so will that really change the, will that motion will be changed, transmitted to any other link? No, it simply slides on the cam. It simply slides on the cam. So that that's why in the gates we have a gear teeth. So if you, instead of this simple disc, if I put some teeth on this one and under teeth on this cam, then if I rotate this link 3 about the O, that motion will be automatically transmitted to the cam. But in this case, this teeth are absent. So when I rotate this 3 about this point O, then it simply slides on the cam 2. So this motion is no way transmitted to any link in the mechanism. So can we say link 3 is a redundant link? So degree of freedom now becomes 9 minus 6 minus 1 minus 1. This is the redundant link. How much? Degree of freedom becomes 1 now. And for example, in the above case, instead of cam, here I have taken this as a cam. So instead of cam, if I take something like this, if I take, this is also a circular disc. This is also a circular disc, and that too I fixed at the middle of this one. Okay, so this is the 1 and this disc is 2. So here disc 2 also become redundant link in this case, and again it here we have 2 redundant links in that case. So we need to observe for any given mechanism carefully whether any redundant link is there in the given mechanism. The next example is parallelogram linkage. So in the parallelogram linkage, for example, if I connect this one and this is 1, 2, 3 and 4 in any parallelogram, what is the property of parallelogram? Opposite sides are equal and parallel. So here link 1 and 3 equal, link 1 equal to link 1 equal to link 3 and link 2 equal to link 4, and these two are not only equal, these are parallel. So when I calculate degree of freedom for this one, what is the degree of freedom for a simple 4-bar mechanism? That is equal to 1. And if I take any point on this one, for example, if I take a point, this point as a something like P, and at a distance L from the O, and if I consider the same point P1 at a same length on the link 4 as a P dash, so when I rotating this link in this direction or clockwise direction, the velocity with which the point P moves is exactly equal to the velocity of this point P dash. Why? Because this P and P dash are at equal distances and parallel to each other. So when I rotating this link omega, this also rotates with the omega, with the omega, same omega, and these two are at a distance, the equal distances. So these two travels, for example, at this instant, this is the delta theta, and this link is reached in this position. P is reached in this position when it link 2 is made delta theta. Then the distance traveled by this P is exactly equal to the distance traveled by P dash at this particular instant when this is a delta theta. So that's why velocity of the P and velocity of P dash is always equal in this case. And let me modify a little bit this mechanism. So here at the middle point, here I will, what I do is I attached one more link parallel to the 1 and 3 at the middle of links 3, 2 and 4 by using a revolute joint. So now I will calculate what could be the degree of freedom. So for example, if I use the same general formula, degree of freedom, then what happens? So what is the n here? N equal to 8. Why? Because, sorry, n equal to 5. Why? We have used some additional link here, and this is exactly at the midpoint of 2 and 4. And what is the P1? P1 is in this case is simply addition of the all revolute joints. How many revolute joints? 1, 2, 3, 4, 5, 6. 6. So what is the degree of freedom? Degree of freedom equal to 2 into 5 minus 1, that is a, sorry, 3 into 5 minus 1, that is a 12. 3 into 4 minus 2 into 6, that is a 12. So 0. That means degrees of freedom is a 0. But if you observe carefully, this degree of freedom is not 0. Why? Because we have already seen, uh, for example, if I consider this instance, so this mechanism is like this. At this instant, mechanism is like this, and this is the link 5, and this is the delta theta, and this is also delta theta, and the distance traveled from here to here is exactly equal to the distance from here to here. That means even though you attached a link here, this link, but since this is a parallelogram, whatever distance this is moving here is exactly equal to here. So when the distance traveled by the points attached by the link 5 is equal, then no way obstructing the motion of the mechanism. That means here when the velocity of the point, for example, this is a P, when the velocity of the point P is equal to the velocity of the point at Q, or distance moved by the point P equal to the exactly distance moved by point Q, then even though you join these two with a link, that link is a redundant one. So it's a no longer providing or restraining this mechanism. For example, in the same case, if I join the mechanism, or if I use link in another way, like this. So if I join link like this, here in the previous case link is joined from a midpoint to midpoint, but here this is from here to here. So in this case what happened? In this case degree of freedom equal to 0, because it become a structure. How? For example, here if I take a point P, this is equal, this link is equal to this one, and this link is equal to this one. okay, and parallel also. If I take point P and point Q, the distance moved by P is no longer equal to the Q, but here distance moved by P is more than the distance moved by Q. Why? Because our velocity of the P is more than the velocity of Q. Why? Because this length is more. What is the velocity equal? Velocity of P equal to length into LP into omega. But this this angular velocity also omega, but distance LQ, here VQ equal to LQ into omega, but here LQ is less than the LP, so VQ is less than the VP. And if the distance traveled or the velocity of the point P and Q are equal, then only this link will become redundant. It won't constrain or it won't oppose the motion. But here in this case, it's not the same. It is not the case. So it is making the entire mechanism as a structure by reducing degree of freedom to 0. The same problem has asked in uh, 2011, but so in the different way. I mean, in the previous one I joined, this is a fixed one, so in the previous joined I link from here to here, but instead if you join link from here to here, is there any difference? This is the midpoint of this one, link 3, and this is the midpoint of link 1. So whether you join like this or join like this, if these joining points are at the midpoint, and not only midpoint, for example, this is if you are joining at a distance x from this point A, for example this is a point, and you are joining at a distance of x from the point A on the link 3, and here if you take at a distance of x from the point B on the link 1, and if you join, even in this case nothing will happen, because whatever distance it travels is equal to this one. So in this way, if you put n number of parallel lines to this link 2 or 4, then those lines are not going to change the degree of freedom of this mechanism. So what is the degree of freedom of in this case? Again, it's a 1, not 0. When will it become 0? If I use the link like a cross one, like this.